Hey guys, in this video we will discuss the solutions of the last homework sheet. And in the first exercise we are given some statements and we want to decide if they are true or false. And in the first statement we are given a divisor and in any algebraic function field. And it is claimed that if degree is the same for any divisor A prime, then we want to decide if they are equivalent or not. Indeed, from the lecture notes, we have the other implication. This is correct. But in general, this is it's not a characterization. Indeed, we can consider elliptic function field. This statement is false. And counterexample can be given by elliptic function field. If we consider an elliptic function field with at least two distinct rational places, let's say P and Q, then by the definition of degree, they have the same degree. But P and Q cannot be equivalent for the distinct places in the elliptic function field because otherwise we can consider a non-zero function which is in the form of whose principal divisor in the form of P minus Q, and this makes this function field rational. But in this case, genus of the rational function field is 0 and the genus of the elliptic function field is 1, so this cannot be possible. And similarly in the second statement, we want to decide that if two divisors have the same dimension, so I mean if the dimension of their Riemann-Roch spaces are the same, again, it is claimed that they are equivalent. In that this is not correct. We can explain it by the same counterexample. And please note that we always, the other, like if we have two equivalent divisors, their dimension should be same, but we don't have the other way around. And again, the counterexample can be given by this, because in the elliptic function field, for the rational places, we know that their degrees are bigger than or equal to 2g minus 1. So their dimension are exactly their degree plus 1 minus g. So they have the same dimension. If this is the case, these Riemann-Roch spaces should be exactly the base field K. But as we said before, as P and Q are distinct rational places, P and Q cannot be equivalent. In the third statement, actually, like all of them are statements can be explained by the same arguments. In the third statement, we are given an elliptic function field with two rational places, and it is claimed that if they are equivalent, they should be the same. And if we suppose not, so that means they are not the same, by the assumption we know the existence of non-zero function whose principal divisor is exactly P minus Q, but this assumption makes F rational function field. We get a contradiction for the genus. And in the fourth statement, it's claimed that every degree zero divisor is principal in any algebraic function field, and this is not correct. In the rational function field, one of your exercise class, you know that the statement is correct. But again, by the same example, when f is elliptic, the divisor p minus q with two distinct rational places is a degree 2 divisor, but it cannot be principal. So the statement is not correct. And in the last statement, again, we are given an elliptic function field with at least two distinct rational places. And the statement tells us the dimension of the Riemann space of P plus Q is exactly the dimension of P plus the dimension of Q. But as we explained in the second statement, for the rational places, we know that they are exactly K. And this is the vector space sum, so the left-hand side should be K. But for the right-hand side, we know that its degree is 2, which is bigger than or equal to 2g minus 1. So its dimension is going to be its degree plus 1 minus genus, which is 1. So it has dimension 2. That means we have proper inclusion. So the statement is not correct. And in the last statement, actually, this is another way of asking the third statement. It is claimed that for a function field f over k, if we are given two distinct rational places, here we suppose that there exists a non-zero constant whose principal divisor is exactly p minus q. Then we want to decide that if the rational function field, indeed, like it was also question in your previous exercise sheet, you can show that its genus is 0. This is the one way. But practically, you can again consider the field extension. F over k of z, we know that this extension degree is determined by the degree of the zero divisor, which is equal to the degree of the pole divisor. And thanks to this assumption, P is the 0 and Q is the pole of z. Indeed, their degree is 1. So we can see that, like, if this extension degree is 1, and if kz contained in F, we can get the equality. So F should be rational function field. In the second exercise, we are given a function field F, and if its genus is 0, then we want to see the existence of a divisor A whose degree is exactly 2 and its dimension is exactly 3. For the solution of this question, let me recall that there exists always the canonical divisor inside of the function field F, and we have the full characterization of for the canonical divisor in terms of its degree and the dimension of its Riemann row space in terms of the genus of the function field. And if genus is 0, degree of the canonical divisor is going to be -2 and the dimension is going to be 0. And now let me set a divisor A as minus omega. In this case, degree is going to be minus degree of omega, which is exactly 2. And the degree, this degree is bigger than or equal to 2g minus 1. Genus is given as 0. So its dimension is exactly its degree plus 1 minus g, which is 3. So the tricky part was to consider the canonical divisor and its characterization in terms of the genus. So this is why there exists always a divisor of degree 2 and its dimension is 3. For the third statement, we are given a finite extension of a function field, which is denoted by f prime and k prime. And we suppose that the extension degree is n. Just recall that for any place in the base field and p prime, which is an extension of p, we have the fundamental equality. And this equality tells us if you consider the all places which lie above the given p, then the ramification index times the relative degree should be equal to the extension degree n. And in the first part, we suppose the ramification degree for these places is exactly, and this is the extension degree, right? In this case, we know that ramification index is an integer, which is at least 1. And relative degree is the field extension of fp prime, residue class field of fp prime, of the residue class field of p in p. So this should be always also bigger than or equal to 1. So this equality cannot be possible if there exists unique extension of p in the extension field p prime and its ramification, its relative degree is exactly 1. And similarly, in the second statement, we suppose that if relative degree and the extension degrees are the same for every extensions, then we should have n distinct places p prime, which are extensions of p, again by the fundamental equality. And in this case, actually, when I was talking about the lattices from function fields, I use the terminology that p splits completely in the extension field, and in this case, p splits completely in the extension field f prime. So we can easily derive these arguments by using the fundamental equality.